Welcome to session 3. My name is Zoe Dillis. It's my great pleasure to be introducing the 3 consecutive speakers we have this afternoon. The first of which is Laura Trethewey. She's an award-winning journalist and the author of The Deepest Map, 2023, which follows the incredible race to map the entire ocean floor by 2030. Kirkus Reviews called it required reading for environmentalists, armchair adventure divers, and those who care about the world's oceans. Her writing has appeared in the Wall Street Journal, The Guardian, The Atlantic, and The New York Times. In 2020, the Writers' Trust of Canada selected Laura for a Rising Star Award. She comes to us from Germany, where she lives with her family. Join me in welcoming Laura to the stage.
Hi, everyone. It's so nice to be here. Thank you so much to David Rumsey for bringing me over from Germany, and to the entire staff for being so great. This is a really wonderful conference. I reached out to David Rumsey Map Center in 2023 when the book came out, and I thought maybe I would get like a Zoom presentation. So the fact that I'm actually here is pretty amazing. So I'm going to talk about the deepest map, and I'm going to display some historical and current seafloor maps, and I'm going to explore this ongoing debate within the hydrographic community over how we connect humanity with the seafloor, and this place that sort of stubbornly refuses to be seen. So I'd like to start off by introducing you to an ocean mapper you may not have met before. This is Cassie Bongiovanni, and she's the hero of the deepest map because she's done extraordinary things that no one in the history of mapping has ever done before. She was the lead hydrographer on an expedition called Five Deeps, and this was an expedition that started back in 2019 to send the first person to the deepest points of all 5 oceans. And the problem was, when this expedition began, we didn't actually know where any of those points were. I mean, we had a good idea of where some of them were, but yeah, we didn't know where most of them were. And I remember finding that astonishing at the time. Like, how do we not know that? How have we mapped the human genome, but we don't know the limits of our oceans? So that's kind of how the book got started. And Cassie gets herself a job on this expedition, going out to find those deepest points. And she's 25 years old at the time. She's the youngest person on the cruise. She's fresh out of university. And she goes away for a year and a half on this privately funded expedition, paid for by a multimillionaire financier, Victor Vescovo, who also paid tens of millions of dollars to build a state-of-the-art submersible to get him to the bottom of all 5 oceans. So that's Victor, and he's standing in front of his submersible on a ship that he also brought. And Victor tends to get all the glory for this expedition because he's now the world record holder. But it's really Cassie, this shy, humble, sort of goofy millennial mapper, who did the lion's share of the work finding him the deepest points to dive. And over the years she spent at sea with this expedition, she and her assistants mapped over 1 million square kilometers of seafloor, much of it for the first time. And this picture was taken in the Indian Ocean, right around the time that she discovered that the deepest point in that ocean was not in the Diamantina fracture zone off Australia, where it was commonly believed to be. It was actually off Indonesia in the Java Trench. So here she is, just kind of casually upending all this foundational knowledge that we have about an ocean. There's 2 quests to map the seafloor that I'm following in the deepest map. There's Cassie, who's on a quest to map the deepest points, but all the maps that she collects, she's sharing with this organization called Seabed 2030. And Seabed 2030, some of you may have heard it called, it's basically an extension of GEBCO, so the General Bathymetric Charts of the Ocean. I think many of people are familiar with it. This organization, it was founded in the early 1900s by Prince Albert of Monaco to map the entire ocean. And Seabed 2030 is an extension of that, and it's really a way to kick the world's butt to get this done by the end of the decade. And this is a map of what that Seabed 2030 map was produced in 2019, around the time that Cassie went to sea with the 5 deeps. And it's a map of what we've mapped so far versus what we haven't mapped so far. So obviously the blue is the mapped areas and the black is the unmapped areas. And this is less than 20% of the global ocean. And what Seabed 2030 wants is high resolution multi-beam. That is what they would consider mapped. It's the highest resolution maps you can get of the seafloor. The majority of the ocean has already been mapped with something called satellite altimetry, but these maps are so grainy. The resolution is around like 4 kilometers. That's the best you can get. And that means that you can lose entire seamounts within them. So Seabed wants high resolution multi-beam maps, and they're gonna make all those maps free and publicly available to whomever wants them. And this map really puts into context what we've mapped and what we haven't. And the big question of the deepest map is, why haven't we done this? And what would it take to finally finish this map? So what does a map of the seafloor look like? This is probably what most people are familiar with. It's a nautical chart of Provincetown, obviously, and you can see that the seafloor here is it's simply a number, and that indicates the depth. You've got a little bit of shading where the darker areas are shallower, the deeper areas are lighter, and then as you get closer to shore, the numbers are kind of going down, getting lower and lower. It's getting shallower and shallower, which tends to happen near coastlines. And this is really helpful for sea captains who want to make sure that they're not grounding their ships on the bottom. But in terms of what the seafloor looks like, there's not a whole lot here for the imagination to chew on. It's just a number. There's no sense of, what it looks like, what it feels like, whether it's sandy or sloped or hilly, whether there's any animals living there, whether there's any seismicity in the area. It's just a number. And these point measurements are probably an artifact of how we measured the seafloor for nearly 4,000 years, which was to drop a weighted line and get one single point measurement. And that changed in the 20th century when the Titanic sank in 1912, and then World War I. This is an early acoustic sounding test with something called an oscillator. It was the first test in 1914 where they used sound to detect the seafloor. But the echo sounder era really took off after World War II. And then suddenly it's possible to collect a survey across an entire ocean. And so the sonar, just to explain a little bit, it's just a two-way travel time that they're measuring. So down, up, sounding the bottom of the seafloor and then coming back up to the ship, sort of like a bat finding its way around a cave by clicking. And so now we're able to create more detailed maps of the seafloor than ever before. And most of you are familiar with this image from Betsy's talk on Wednesday. This was published in National Geographic in 1967, and it's a map of the Indian Ocean, and it's drawn in a physiographic style. So this is at an oblique angle where if you removed all the water, this is what it might look like if you were flying over the ocean in an airplane. And this map remains one of the most influential maps that we have of the seafloor. And I would argue that the map is so influential, not only because of the scientific significance, which I'll get into, but also because it portrays the seafloor as a landscape. So this is, a place you might explore. Maybe you're not going to go for a picnic here, but it's a place that you could potentially traverse, even though it would be incredibly hard to reach the bottom here, and only a handful of people have ever done it. So I love this picture of Marie Tharp too. This was also in Betsy's talk the other day. I like to bring up Marie Tharp when people ask, what's the point of ocean mapping? Why are we doing all this? The woman behind that map of the Indian Ocean in the National Geographic, she did incredible things for ocean mapping as well. I know that Betsy covered a lot of this on Wednesday, so I'm just going to give a brief overview of Marie and her work. She was a cartographer at the Lamont Doherty Earth Observatory in New York during that post-war Cold War period. And she's a pretty curious character for her time. She's a divorcee. She's working in science at a time when women were not allowed in the sciences. She was at Lamont Doherty, where women there were not even allowed to set foot on the gangplank of their research vessels. But Marie manages to get around those restrictions by forging this sort of part scientific, part romantic partnership with another scientist called Bruce Heezen, who goes out and collects the soundings at sea, and he brings them back. And she painstakingly plots them on a map. This is her at work. And one of the first things she notices is that there's this big ridge in the middle of the Atlantic, and it immediately dawns on her that this must be evidence of continental drift. Now, today we all know that continental drift is true, that there was once a big supercontinent called Pangaea, but back in the 1950s, in American geological circles, it was really a career killer to believe in continental drift. People who did, scientists who did, were called drifters, which was like a really sick burn at a American geological mixer in the 1950s. Yeah, but Marie doesn't care. She keeps drawing her maps, and all these new soundings are pouring in thanks to the Cold War and anti-submarine warfare. And she's finding more evidence that the ridge is not only in the Atlantic, that it's in the Pacific, the Indian, it's all over the world, in fact. And then we get this map in the 70s. Eventually, Marie and Bruce would put this together, and here you can clearly see the mid-ocean ridge running all over the world. And when this came out, it was a pivotal moment in the debate around continental drift. And then there's also this new emerging theory of plate tectonics. And so this really paves the way for the general public and scientists, some scientists too, to accept that this is happening, that these two theories are true, and that the seafloor is not dead, boring Earth, but it's actually on the move and very interesting and made up of all these trenches and canyons and interlocking plates. So Marie's maps really gave us a view of the seafloor and changed the way we understood the planet. Now, of course, with anything so popular, you're also going to get some haters out there. And this is Bob Ballard at a TED Talk in 2008. And if you don't know Bob Ballard, he's really a towering figure in the oceanographic community. He discovered the Titanic, among other things. And he's got the Tharp Heezen map, world map up in the background. And he declared that this gives you a false impression that it's a map. This is not a map. And Ballard really captures the main criticism that the scientific community has with this map, which is that you can't use it to find anything, really. A group of scientists in the 1980s tried to do that. They went looking for a rift valley that was on the map in the South Atlantic, and they found out that the valley was actually 150 miles away from where it was supposed to be on the map. And there's a good reason for that. When these maps were produced in the 1960s and 70s, there was more data and better data than ever before, but that's a pretty low bar for the ocean. The data was still pretty sparse at that time. And so echo sounders allowed for this creation of complete survey lines across an ocean. And so on the left here, we see Marie Tharp's work in the North Atlantic with these east-west profiles all the way across. And you can see the sort of two survey lines down there. And then we've got this great quote from her that really explains the situation that they're working with back then when she says, "The echo sounder depended on the ship's electric power, which went off whenever someone opened the ship's refrigerator. When that happened, no echo returned, and the sounder recorded depths as bottomless as the crew's appetite." So it was early days for ocean mapping, and things could go wrong. And the North Atlantic had a lot of survey lines, so there was backup. But in the South Indian Ocean, there was a section more than 4,000 miles long between Antarctica and Australia, and there was only one survey line across it. And that meant that Marie Tharp had to interpolate or make up what was in most of that area. And to be fair, this isn't that different from what a lot of map makers have always done. You know, they put a cartouche over a gap in the map, or they put a dragon on top of something they haven't explored yet. And they have to do this because without papering over some of the gaps in the map, you're never going to be able to complete a full world view until it's finished. And when's it going to be finished? We don't know. The problem with filling in the gaps in the map is that when people look at this map in the 1970s, And even when they look at satellite mapped images of the seafloor today, they assume that we have this whole ocean mapping thing under control and that we've mapped it all. When it ends up hurting organizations like Seabed 2030, where they're really battling this perception that the job is done, and it's not done. It's nowhere near done. So how do we map today? We use these something called multi-beam echo sounders that I mentioned before. And as you can probably tell from the name, instead of single beam echo sounders, they have many beams. And they project a fan of sound underneath the ship, and they're able to get a much broader view of the area. And all of a sudden, we're able to see sort of like a view of the seafloor, when before it was maybe more just a profile. And so multi-beams are light years ahead of lead lines and single beam, but they're still incredibly costly and time consuming. Costs about $50,000 a day to send out a survey ship. And an ocean mapper has to go out for days or weeks or months at a time, and they travel really slowly, like 8 to 10 knots. And they do what's called mowing the lawn. So they just kind of go back and forth in sections and cover it off piece by piece, which is what's happening here. This is an Inuit community in Nunavut, Cambridge. It's called Cambridge Bay in Nunavut, Canada. And for one of the chapters in the Deepest Map, I went up to this community and watched hunters there mapping their waters. So there's a lot of uncharted waters in the Arctic. And so they were going out day in, day out and mapping this bay. And you can see they're about halfway done, and they're lucky. At the end of the day, they get to go home. They live like right there. But most of the uncharted water is in the middle of the ocean. And so you're out there for like a good long time. And this is usually what those multi-beam surveys are creating. These are rainbow color maps. And this is what Cassie Bongiovanni would be making today. This map was created during the search for the downed Malaysian Airlines flight in the Indian Ocean. It created one of the largest multinational searches of the Indian Ocean ever. The Indian Ocean is the least understood of all 5 oceans. It was pretty much ignored scientifically up until the 1950s, late 1950s. So incredible things were found during this search, including 2 19th century shipwrecks. And this view shows the Diamantina escarpment, which is the largest seamount in the area. And there's seafloor spreading going on that's creating this trough. And there's some extinct volcanoes in the front there. And there's just incredible detail. However, like the Marie Tharp maps that I showed before, there's also a lot of controversy about these maps. This map is exaggerated vertically 3 times. And the main reason for using vertical exaggeration is because the scales are so huge that mappers are working with that even a huge feature like the Diamantina escarpment would basically disappear. It wouldn't stand out at all. But sometimes vertical exaggeration goes too far. And this is a good example of that. It's from an expedition in the Great Barrier Reef where they discovered a 500-meter tall detached reef. And the visualization didn't state its vertical exaggeration, but the point is so exaggerated that it looks almost ridiculous, this little tiny thing. One biologist called it Tolkien-esque, which I really loved. And you can clearly see that there's some floating red data here where they stretched it so far that they started to pull in LiDAR or something else, some other data. And vertically exaggerated images like this, they look cool on a press release, but you can tell that they're just not a reliable look at the seafloor. So here is an example on the left of why color maps are often hated by some in the visualization community. So we see Marie Curie, the Earth, and an apple covered with the rainbow maps. Does anyone want to take me through maybe why this is not the best visualization of these objects? Yeah. No, it's not intuitive, yeah. It creates a lot of artificial boundaries where none exists. So there's all these greens and reds that are creating boundaries on the face and the apple and the earth that are just not there. They're also not effective for colorblind people. And people don't really have an intuitive sense of what the colors mean. So like, why would a deeper part of the ocean be blue and a shallower part is red? It doesn't really make a lot of sense. So what's up, what's down, we don't know. Instead of rainbow maps, visualization experts recommend using these colors on the right for the ocean. So you can see that they've got ones like depth and density and turbidity, and these correspond more accurately to data values, and they often don't create these artificial boundaries, and they look more continuous and intuitive. And this is what it looks like in the deep sea. This is a great map that Robert Simon made for me this morning that shows the same Diamantina fracture zone, but in the more natural depth shadings that we were talking about that are recommended by visualization experts. And I don't know about you, but I find this quite relaxing and realistic to look at compared to the rainbow maps. So this is a map that Cassie Bongiovanni made in the Philippine Trench. And despite all the criticism of rainbow maps and vertical exaggeration, both continue to be really popular within the community, the scientific community. And this could be because a lot of mapping software just tends to have that as a default. But the other reason is that it probably just looks cool. Like it looks really sciencey. Yeah, and it portrays the ocean floor in this sort of hallucinogenic sweep of colors. It looks very bright and bold and extraterrestrial, which would also make sense because exploring outer space is way more popular than exploring the deep sea. So anything that kind of hints at outer space is always a good thing. And these rainbow maps look cool, but I would argue they don't look very inviting. They don't extend an invitation to explore the same way that Marie Tharp's physiographic maps do. I can't imagine wandering around in a rainbow map unless I'm like dropping a hit of acid. There's no way. So ultimately, what I think all these controversies point to is that the deep sea is an environment that is better heard rather than seen. And that's a problem for humans like us. We're very visual creatures, and we place a lot of importance on how things look. And in that way, seafloor maps are always going to be quite challenging for us. Because no matter whether you're using a nautical chart or you're using a rainbow map, it's always going to be butting up against someone's preconceived notions of what the seafloor should look like. So to circle back to Five Deeps and Victor Vescovo and his expedition, so the multimillionaire financier, when he went to the bottom of the very deepest point in the ocean, the Mariana Trench in the Pacific, he went down 48 million in his $48 million submersible, sent up a cloud of dust, and he could barely see 10 feet in front of him. Like just, it was very turbid that day. And I thought that was a really ironic ending to this whole story because he had spent all this money and gone so far around the world. And then when it finally came time to see the very bottom of the ocean and to like survey what he had explored, there was no great vista there to look over. It was just sort of black water. So I think sometimes the ocean floor just sort of refuses to be seen. Seabed 2030, meanwhile, this is their latest map from this year. They continue to sort of chug along, and every summer they release new maps. And in the early days, they were making a lot of great progress. They were releasing big leaps and bounds in how much they were getting out of different countries. They would ask them to share maps, and they would release this from their vaults. But recently, the project has sort of stagnated in the mid-20s, so they're about 27% mapped now. And so this is, you can see this as a big update from the last map in 2019, but it's still, we're far off from finishing it. And there are a lot of reasons for this. There was COVID delays, there was funding issues, but the political situation is also really different today than in 2017 when Seabed 2030 began. We're in a way more fractured and unstable time, and wartime can often be a boon for mapping. We've seen that over the years, that technology gets developed, but the innovations tend to kind of stay within a country. They don't necessarily lead to a lot of collaboration across borders. People don't necessarily want to share maps. And that's a real hurdle for Seabed 2030. So even without all these hurdles, though, I'm skeptical that Seabed 2030 would have made its goal, just because we don't always have a really really big desire to see at the bottom of the seafloor unless we have a good economic motivation to do it. And I think that's a pity because, as Marie Tharp showed, a good map can change not only how we understand the ocean, but also how we understand the planet and the place we call home. All right, I'm going to leave it there. Thank you.
Great job. Do some questions now. All right, we've got 6 minutes for questions for Laura.
Thank you. That was great. On that last map that you showed, I have a couple questions. What is the red versus the blue? And can you say anything about, it's obvious why some areas are mapped first, but what are some of the other reasons for some of these spots that have gotten mapped?
Oh, that's a good question. So I actually don't know what the red is. I just took a look at this map today, but the blue is obviously where the mapping has progressed. And you can see that most of it is transit lines, so shipping lanes between continents. And you can see around Europe, there's really good maps. You can also see different places off of Brazil that have really good maps. Places in the middle of the Pacific have really good maps. And I think that those are often created by, I mean, the middle of the Pacific, there's some seabed mining projects that are happening out there. So mapping is getting pretty good out there. And basically, like a lot of the maps where you're seeing developments are just countries deciding to take on certain projects. So the military has decided that an area is super important, or maybe there's some kind of, kind of new biological discovery that's happening. A lot of this is like oil infrastructure. So yeah, I mean, that's basically what we're seeing here. There's kind of a story behind each of the different areas. You can see the Mediterranean is really well mapped. We're doing good there. But basically, I think what you can take from this is that the countries with a lot of money and resources are the ones that have the best maps. And that tends to be in the Northern Hemisphere. And the bottom part of the world, the Southern Hemisphere, has the least maps. So it's kind of what we're seeing.
Hi. How do you deal with mapping in those coastal regions where like the depth may be limited, like it's too shallow, or in regions where like a kelp forest might inhibit you from mapping in that region?
So the question was like, how do you deal with different depths?
No, like the limitations, like the navigational limitations, like if a ship were to go near a coastal region where it's too shallow for it to go, how do you deal with mapping in those regions? Or if there was like a kelp forest that was inhibiting it from going in that area?
Oh, okay. That's a really good question. So one part of the book, I deal with crowdsourcing initiatives, which are basically trying to tackle some of those areas that are really hard to get to for a survey ship. And so there's a really great project that's happening in the Great Barrier Reef where they just put really simple echo sounders on boats, and fishermen go out, and while they're crisscrossing the Great Barrier Reef, they're collecting maps. And this is an area where like James Cook and other explorers would basically like run aground on a coral reef, and there's no way for survey ships to get through there. And that was also what was happening in the Arctic Ocean with a lot of the Inuit hunters that I spoke to. These are areas that often are blocked by sea ice most of the year, and so ships just can't get in there. So that's one way to do it. And then there's also a rise in drones. So there's actually a big company here in Alameda called Sail Drone, and they are working with sending out drones that can do incredible things. One ocean mapper called what they're doing black magic for ocean mapping, because they've been able to go around continents, they've been able to go across oceans, and so they're getting into hard to reach places that have never been mapped before. And that's really like the next stage that we're getting into this automation and AI stage where drones are going to be doing a lot of this mapping, which I find kind of sad. I'm a romantic. I kind of like to think of people out on ships doing mapping, But that's probably the wave of the future.
Do you have any newer book recommendations for my mom, who's a retired physical oceanographer?
Oh, yeah. Yeah, I think there's a really good book out called The Blue Machine. I really love Susan Casey's book. The new one, I think it's called The Underworld. That one's wonderful. Yeah, Betsy's book, All Over the Map. Yeah, I also love Helen Scales, who wrote The Brilliant Abyss, and she also does really wonderful things. So come and talk to me afterwards. I'll probably think of some more in a couple minutes, but those are my favorites.
Hi. This is really exciting because I am currently studying physical oceanography and specifically how bathymetry controls ocean flow. But my questions maybe has a little more to do with how the international collaboration of this works. I think it sounds like people have done lots of surveys and with different motivation, and it just, to me, seemed like a really big hurdle to assimilate all of these data. I was wondering if there's any international collaboration or major projects that are targeted on mapping the ocean floor, and if not, then how are the maps that we see today, how good are they in terms of assimilating all of the data that we've ever collected in the past?
Oh, that's such a great question. I'm saying all the questions are great. They are. So there's 5 different centers for Seabed 2030, and they're situated in different parts of the world. And at the end of every year, they get all their maps and they stitch them together at this one place in Southampton in the UK. And there's one woman, like Pauline Weatherthall, that's her name. She didn't want to speak to me. She doesn't want to speak to, she doesn't do interviews, but she just sits there and stitches all these maps together. And yeah, I mean, like, it's really on a case-by-case basis. Seabed 2030, they've really focused on recruiting people from different backgrounds. So in the past, hydrography tended to be really people from the Northern Hemisphere. And so people were going to the Southern Hemisphere and asking them to open up their vaults and share maps. And that just kind of reeked of colonization, and also just people were skeptical of, like, who is this person who just walked in and wants to see maps of all our territories. So they've really tried to work on getting people in different countries to be ambassadors for Seabed 2030 and to work and get those maps out of vaults and to share them into the bigger map. Always with the clarification that these maps are not going to be used for, you can't get a really good look at, like, the entrance to a harbor or something like that. So it's not going to be anything that's going to conflict with national security issues. So I hope that answers your question. It's basically just trying to bring in more people. Somebody at the University of New Hampshire, she works with all of the Atlantic and some of the Indian Ocean, and she's got one of her mappers from Mauritania, I think. Anyways, and that person is sort of her ambassador who goes out and gets a lot of those maps. So that's often how they work, is they try and have a really big tent to bring everybody in.
Thank you, Laura.
Yeah.
Okay. The next person in our wonderful program this afternoon is Ved Chirayath. Dr. Ved Chirayath is the Vetlesen Professor of Earth Sciences, Mechanical and Aerospace Engineering, and Director of the Aircraft Center for Earth Studies at the University of Miami. He is a National Geographic Explorer, 2024 Moore Inventor Fellow, and the founder and former director of the Laboratory for Advanced Sensing at NASA Silicon Valley. Chirayath's research focuses on inventing, developing, and testing next-generation sensing technologies for observing the natural world. He invented NASA MIDAR, fluid lensing, and NEMONET, which we'll hear a bit more about. He received his BS, Bachelor's of Science, Master's of Science, and PhD in physics, astrophysics, and aeronautics and astronautics from Stanford University after 5 years studying theoretical physics at Moscow State University in Russia. Please join me in welcoming him for his presentation entitled Inventing NASA Space Exploration Technologies for Our Blue Planet and Beyond.
Thank you so much for having me. It's a real delight to be back here. I spent about 12 years of my life in the Bay Area. My PhD advisor, actually, I see Professor Juan Alonso here. I just want to share before I start this talk, literally none of this would have happened if it were not for his belief and support in me. So if you just give one round of applause to my advisor, I'd appreciate that. Sorry to embarrass you, Juan. Tables are turned now. All right. I am going to talk about some of the technologies I developed to map our seafloor. This has been a very humbling experience to see the depth, and I'm constantly feeling out of depth. I am still an astronomer in recovery, and three main questions that drive my research and life are, first, how do we detect life? How can we better explore Earth to preserve and protect life as we know it? And how can space exploration tools benefit the ocean? Now, as a NASA inventor, I spent decades inventing space exploration technologies to explore space to answer these questions, and something deeply troubled me from the very beginning, and Sylvia Earle had a hand in pulling me over to the blue side. This is now, thankfully, cliche. I have mapped, actually two of these images are mine when I was doing the space side of things, but the technical disparities that exist between what we can do in space and what we can do on Earth are really startling. We lost a probe on Mars the size of a golf cart. It took about 9 days to image the crash site in detail. On Earth, we've lost jumbo jets with hundreds of souls on board, and a decade later, we still can't even find where that is. That's the scale of difference. If you think about how Hubble and Webb Space Telescopes have changed our understanding of our place in the universe, that is exactly what we need for oceanography. We need a space telescope moment. James Webb Space Telescope can look that direction, about 14.5 billion light years. It costs roughly $14.5 billion of our taxpayer money, so that's about $1 per light year. We can't look down about 100 meters in the water. So you can see that there's an urgent need for this, and the moment really is now. The ocean is bearing the brunt of climate change. It is undergoing the most rapid changes, and it's happening out of sight, out of mind. It's a world in peril. This is a marine heat wave in Florida, where I live now, and the third largest barrier reef in the world. It suffered basically an underwater wildfire where corals bleach, they die. These organisms are the source of the leading drugs to treat COVID. So you were all partly benefited and saved by marine organisms you've never heard of that are going extinct on our watch due to the pressures we're putting. Without any baseline data about what's happening in the ocean, we lose these things at our peril. But the ocean also teaches us about our origin story. These are, does anybody know? Stromatolites, yes, thank you, geologists. These are your distant ancestors. You actually have them in your genome and in your gut right now. They terraformed our world. They're the original climate change organisms. We went from 0% free oxygen over a course of around 3 billion years. They oxygenated our planet to support complex multicellular life. And as a space agency looking for life, this is really what you're looking for. You're looking for an organism that is capable of terraforming planets. Humans have accomplished it on a pretty short time scale by putting lots of carbon in. These guys accomplished it first, and they set the stage for life to grow to epic proportions. We are incredibly lucky to be now alive in this era of giants, whales, creatures that are their own spaceships, but also creatures that, hopefully you can hear that. These are species that, like humans, can communicate over vast distances, but they don't need technology to do so. So if you're looking not just for life, but intelligent life, it behooves us to understand the depth and diversity of life we have on our planet and how we might communicate with what turns out to be one of our nearest relatives. The ocean also teaches us that acoustic communication may not actually be the main form of communication in the universe. Certainly on Earth, the dominant form of communication, over 90% of species communicate using light, bioluminescence. That is alien to us. We're just beginning to understand how that signaling works. It helps us look for life elsewhere. And in that regard, we hit the celestial jackpot. This is actually a paper I wrote with my collaborator, Dusty, you heard from earlier. We are redefining what is the search for extraterrestrial life to really become the search for extraoceanic life. In our solar system, we have multiple ocean moons. These are not to scale, but you can actually see sunlight glinting off of Titan there, off of a liquid hydrocarbon sea, and that's a real picture in the infrared. Europa is one of my most tantalizing, exciting targets that potentially has a liquid ocean larger than Earth's under an ice sheet and is, I think, ground zero for where you want to go find cool living organisms. So I grew up in Southern California. That was my pet rat, dog, first makeshift telescope, and I was really obsessed about the ocean and life. I wanted to work at NASA desperately, and I got my dream job founding and directing the Laboratory for Advanced Sensing in that building in the bottom right, down here at the road, NASA Silicon Valley for 10 years. And while a PhD student here and a scientist there, one of the questions I tried to answer was, how do we see underwater? Why is it so difficult? What are the challenges? The first is just there's not much to work with. All the light we have coming down from the sun through the Earth's atmosphere is attenuated a little bit by the atmosphere, except in the radio. You can see there's a big window in the radio wavelengths where we use GPS, cell phones to communicate. In water, unfortunately, everything to the right of red light is highly attenuated. So in the first micron of the sea surface, it's gone. And on the left-hand side, it's also highly attenuated. So after you get from ultraviolet and beyond, there is a little X-ray window and some gamma windows, but these are very high energy photons. Basically, there's not much light. And the light that does penetrate the blue bands, they go down to about 100, 300 meters maximum. And then there's almost complete optical extinction. So this is one challenge, is attenuation. The second is that we're looking through two fluids when we look from aircraft or spacecraft down at the ocean. You're looking through air and you're looking through water. And where those two interfaces meet, there's a refractive index jump. Light does not behave nicely and it bends and morphs around. You get refraction. You see this if you put a pencil in a glass of water. This is a big problem because a lot of our spacecraft, aircraft look at Earth and they don't look at Earth's oceans straight down, right? They look at it at a slight angle. So even if the ocean were completely flat, you would get a case where you cannot actually pinpoint where something is with accuracy from space or aircraft. And you can see this if you scroll on Google Earth on your phone through time. Things on land will appear to be stationary, but underwater they might shift around because we did not refraction correct any satellite imagery. The second issue is the ocean is never flat, despite how much I would like it to be when I'm at sea. So you get waves that cause very high level distortions. Those can distort the view of what you see underwater, sometimes to 3-4 meters resolution, sometimes worse. So I set out to try to simulate this and study this in a controlled environment. I call this phenomena fluid lensing, the effect that ocean waves have on light as it bends it. There's a couple interesting things that they do. If they're the right shape, you'll actually see that if you slow this down, waves can magnify and demagnify objects underwater. You'll also see the formation of these bright bands of light in the background. Those are called caustics, and they're actually coming from those lenses of light being focused at the seafloor. So I created a technology called fluid lensing and a hardware instrument called Fluid Cam that tracks those magnification events and the caustics to see very deep in the water column and at high resolution. And then I started going out in the real world and testing this on aircraft. So we flew drones around lots of different coral reefs around the world. This is a reef from American Samoa in 2016. And you can see here a fringing coral reef with lots of hard, stony coral. This is the view from the aircraft. So in addition to refractive distortions, you have strong reflective distortions. And this is the fluid lensing view, which in this case was validated down to about 0.5 centimeter in 3D. So we get a sort of diver scale view of that reef environment, which would take teams of divers, which we were working alongside, a very long time to survey. And to give you an idea of scale, there's a sea cucumber that will pop up here. That's about this big. So since then, lots of things happened, global campaigns, COVID, a lot of the oceanographic community was pushing me to try to look through breaking waves, and I said that's not possible, but I spent a lot of time developing sort of a modification to this with my team, and we came up with a way to see through the majority of breaking waves now with fluid lensing, so we can see to depths of about 20 meters plus, roughly centimeter resolution, depends on sea state, and we can create very detailed 3D models of reef environments in particular. This data set I'll show on the screen afterward. You can dynamically zoom in and play around with it. This is about 120 terabytes of raw data for just an area of 5 square kilometers. We've mapped dozens of places, so you can do the math. We're at the petabyte scale in terms of data. And in many cases, we are discovering things every single day. My students spend most of the time with the data, and they just keep coming up with new things. Tires, skeletons, corals that have moved, diver tanks that were dropped on things. This is a time series of one of our sites in Guam, captured by our team there, a full year of a reef at the centimeter scale, every single change at 14-day intervals. So it's giving us that first remote sensing view of the underwater world, just like we do for land management. And we're starting to just build the tools to analyze that. One of the tools I built is NemoNet, and I'll play a short video about how NemoNet works.
NASA NemoNet is a game where you classify the world's coral reefs by painting on real-life images scanned from the ocean floor using a revolutionary instrument that lets us see beneath the waves at unprecedented resolutions. Our oceans are so vast, it would take us 2 million years to classify the world's coral reefs by hand. The classifications you create are sent to our teams of NASA scientists at home base to teach our supercomputer to classify coral reefs on a global scale.
So that project launched during the pandemic, 2020, and we had about 100,000 sustained users. At peak, it hit around 3 billion page hits. Everyone was stuck at home, nothing to do. So they classified lots of reef for us. And Betsy had mentioned there was a group that worked 4 years on a map. The product I'm about to show you, we're just as in journal review. We worked about 15 years on this technology and this method to go from a picture like this, which is, again, you're looking at hundreds of terabytes of data, to a habitat model for that entire reef. And this is really pioneering work that's led by one of my PhD students, Sufyan Bouchlagam. Is currently in Rome at the moment, but you'll be able to interact with this map on that screen and zoom in down to see a coral at the centimeter scale. If you dropped a cell phone anywhere on that reef, in any depth, you could find it. That's the scale of that map. And we built a data viewer to kind of explore it. We're learning how to manage maps. I'm not a map maker. I'm learning that map is a loaded term, but I prefer imagery. So this is multispectral imagery of a reef surface, and then translating that into a habitat map that tells us semantically what you're looking at. That's really the bread and butter of what we do for passive remote sensing on land, understanding what we see. And once you do that through time and you're able to pinpoint a coral and go back to it from aircraft or spacecraft with geoprecision, right, you now look at changes in those reefs and see down to each individual taxa, right? Not taxa, I would say class. These are more geomorphological classes. How those structures are changing as a function of us, right? Of human contributions and impacts to those environments. One thing you will not see when you explore the data set, however, when you zoom in, are any fish or animals in the reef. And that's not because they're not there, it's just a byproduct of fluid lensing's integration. It deletes every stray photon that is not seafloor. And so this was a problem that was brought to my attention from the very beginning, and I kept putting it off. Finally, did a little prototype of a project and then handed it over to much more competent students to develop a new automated detector for wildlife. And now for that entire reef, thanks to the work of my students Noah and Jesse, we have the first kind of prototype wildlife detector for an entire environment. And this is an automated system that goes back to the raw data, compares it to the fluid lensing solution, and can actually pick out autonomously every single thing on that reef that moved. That's down to this scale. And again, 100 terabytes or so, very small animals. This is a fever of rays at the bottom there. We can geolocate where they were, when they were. We can make novel detections. We did not see any of these things. That's our dive team on the right doing the underwater survey for validation. But it's starting to reveal a very different world than we see from our traditional diver surveys in the water, where the presence of divers, the boats, scare away all the large pelagic animals, right? You don't typically see the sharks or the mantis because they're long gone because you've been splashing too much. So from these data, we are really getting a new view of this and being able to understand and go back to all the historical data sets that we've gathered and pull out that measurement. I've also been thinking about scale. So contemporaneous with developing the sensing technologies, the sensor is really only as good as the platform that carries it. And right now, drones just don't have the endurance I need to do what I want to do. So we've been working with a number of different companies. This is Swift as part of a NASA project to develop long endurance solar powered aircraft. This one's carrying fluid cam and can fly for about 3 months at a time and do high altitude observations in over one spot. So they're filling in this gap that satellites can't quite do. Lower altitude drones, we actually just tested this here in California this summer. We've been building with a company in the Netherlands a long endurance vertical takeoff and landing drone that flies for about 4.5 hours over the sea. Fortunately, the warranty doesn't cover incidents over water, which that's like, no, that's all they do. But we've been testing it, building up its capacity, and this will be, coming hopefully to a sea near you to map coastal regions. I've also been partnering with Stanford colleagues here at the Goldbogen lab to test this technology on a different environment. This is landing at sea in Monterey Canyon.
Nicely done. Hot dog. Holy cow.
And that is yielding really brand new data we've never seen about whales, these creatures. That was a lunge feeding event. This is actually like a 16K video if you want to really dive in, but I can't display it on the screen. One of the challenges with studying these organisms that to me are the apex of what we want to find elsewhere, intelligent, sentient animals that communicate and have culture, is right now we are hitting them left and right with ships. We just don't see them. And it seems difficult to imagine, but acoustically you actually cannot see them. There's a dead zone, acoustic waves refract down away from the whales. The whales spend a lot of time at surface at nighttime. They're feeding there. There's collisions with cargo ships. The cargo ships don't fare very well as these are 100-ton animals at 120 feet across. So I've been looking at using fluid lensing to not only detect where and when they are at depth, but also provide clear pictures of the animals. This is a humpback in Monterey Canyon that's got a suction cup tag from the Goldbogen lab there and a fluid lensing result. I just went to Antarctica in February with that same team, and we were testing out these technologies in a planetary analog environment that looks a lot like Europa or Enceladus, but also is filled with whales. And we actually have some of our first fluid lensing results of humpbacks there. This is a fellow logging. And this is the first kind of fluid lensing view of that individual. And we're learning is that we can actually get very, very detailed pictures of what's on them and their fingerprints that are unique enough to identify individuals. So there's very few whales that actually put their flukes up to take a picture of and identify individuals. This is one technique that might allow us to survey at scale who is also there. And to understand kind of how their lives are changing as a function of a changing climate, we're also trying to make measurements of their body size in 3 dimensions. So this is the first kind of 3-dimensional view of a humpback from fluid lensing, early prototype. But this can eventually tell us how much our krill fishing is impacting their diet, how much are they actually thinning out as a result of human pressures. We also made a couple of other discoveries that we're busy working and publishing, but one of them was the contemporaneous thermal infrared imaging of these whales with fluid lensing to see thermal heat windows. So one question in biology is, as you get big and you're a mammal, you have a lot of heat. And the scaling laws of physics work that the larger the volume you are, your surface area to volume ratio changes. And so as a result, like elephants, you need to shed your heat through big ears that you can fan and pump out heat. With whales that are really well insulated, one question has always been, how do they shed that heat quickly? And we're now discovering that they have thin layers of blubber, and they actually have little heat radiators that they build onto their skin, and they can shed that heat even in places like Antarctica, where you'd think they'd be cold, but they're actually quite hot because they're feeding. All right, so the deeper folks in the audience will be like, this is all well and good, but you're still looking at the skin of the surface, right? This still needs sunlight, fluid lensing. So maximum, theoretically, fluid lensing could go down is 100, 300 meters. We haven't yet demonstrated that. But the average depth of the ocean is around 4,000 meters. That's one big problem. The second problem is we still look at the ocean like our relative here, the lemur, the first simian to develop trichromatic vision, so a third vision receptor, to determine whether fruits are ripe or not. There are no ripe fruits in the ocean. It's a terrible way to look at the sea, like humans do. We have to instead put ourselves in the place of creatures like a mantis shrimp that look at this giant clam and see it in 12 fundamental colors, all 4 polarization states, and ultraviolet. So that's really what we need to start imaging the ocean in. And that's what motivated me to develop a follow-on technology at NASA called MIDAR. This is an active multispectral imaging system that uses lasers and light-emitting diodes to replace the sun and illuminate an object with structured light. So essentially, I went and found every single chemistry that we could across the electromagnetic spectrum, focusing on the bands of light that penetrate water the deepest, so primarily ultraviolet, blue, and a little bit into the green. These were integrated onto an aircraft. This is showing an early MIDAR slowed down so you can see the pulses of light, and then this is sent out over the reef to survey the entire thing at night, which is a completely different picture from day. So just remember, all the data I've shown you so far is just half of the cycle, right? We're missing this other piece of the ocean at night where there's a huge wildlife migration, whales feed, it's super active, all the sharks come out. What instruments like this are showing us is, sure, you can image the ocean in red, green, and blue. You can even do it in other frequency bands, in the visible bands. But if you start looking at it like the animals that live there, in the ultraviolet, in the far blue, like that picture in the bottom right, on the top of that coral, there's actually a disease that's only visible in that wavelength. And so we're starting to see the ocean with this sensor for the first time, kind of the ways that we imagine fish that live there do. And it's allowing us to do some other cool things. Recently, we did a project at our research island at Broad Key. This is in Florida. And we are looking with these 2 technologies at human plastics, trash, and bombs. There are bombs dating back to World War I that are scattered around shallow environments. A lot of them are live and could go off at any time. And sometimes people are snorkeling and spear gun the wrong thing, and kaboom. So one of the projects we just finished is, could we use this technology to autonomously find, using aircraft, bombs that we've systematically placed there? These are inert bombs, I should point out. And we did that recently at our Broad Key research site. So this is one little area zoomed in from the fluid lensing picture. We found 2 sunk boats over there that we didn't know about. So if anyone wants to go salvage those, I don't think there's any treasure, but you could help clean up a reef in Florida. And here you can see 2 inert mortar munitions that are hiding out in the shallow regions. This is one of the reasons why finding munitions is so challenging. As they spend longer in the water, they get covered in biofouling. Algae grows on them. They're very hard to distinguish unless you can see in 3D without wave distortion or caustics, and that's the view we're starting to get with fluid lensing there. And with MIDAR, we're improving upon that in multiple wavelengths. So the top there is the passive fluid lensing result. This is now the active MIDAR product merged with fluid lensing. And of course, we can see that in multiple different wavelengths, which allows us to train AIs that are good to classify where are all of these bombs and autonomously find them against a very cluttered background. So in that figure A there's actually a decoy target that's a pipe that looks like a bomb but is not a bomb, and we can separate those out with a relatively high precision. More recently, more invention fellow, I've been working on what I call the holy grail of this field, what I view as what we need to really map the seafloor. I know different people have different interpretations of map. To me, when I show a picture of we've mapped Mars or the sun, I'm talking about multispectral imagery. In physics, the higher the energy of a photon, typically the more information content it has. And acoustic surveys alone, bathymetry surveys alone, don't tell you what that blob is, right? You need multispectral data. That's how humans do it. We use our eyes to infer through multiple cues what we're looking at. So I want to map not just the sea surface, I want to get deeper with MIDAR, eventually full ocean depth, and combine these two technologies to see at that 4,000 meters from aircraft or spacecraft and see what's on the seafloor. I may not accomplish this during my grant cycle of 4 years. My students will probably be the ones that figure it out, but we've made some big inroads on this, and you've already started merging these two technologies to see things that we've never expected or seen before. So stay tuned. I hope I can inspire other people to come from space exploration and astronomy into this field. I need help. This is not trivial optics or physics, new ideas, new wavelengths. I'm looking at everything from gravimetry to neutrino scattering to gamma rays. I tried to X-ray the ocean and my permit was not granted. But really, what can we do in that wavelength regime that we have in nature to understand what's on the seafloor? One big advance I'm excited about that is your taxpayer dollars at work is a new fluorescent LiDAR instrument I'm building with my partners at BA Systems. I can't show the actual instrument, that's export controlled, but I can show you the schematic of how this works. And this will be flying in another year or two on our helicopter, surveying the ocean down to about 60 meters depth, but not just in one color. We're using two water penetrating laser sources, one at 355 nanometers and one at 532 nanometers. So roughly bluish or UV and green. And these bands can actually stimulate fluorescence, which occur in a lot of marine species, particularly coral reefs, and tell us a lot more about what we're looking at rather than just where it is spatially and how deep it is. So hopefully through some of the technologies I shared with you today, you see that this field is changing, but make no mistake, we're a long ways away. And sometimes I hear a lot, these technologies don't exist, we can't do this. No, they do, and there's a lot more progress we can make. It's really just a matter of willpower. Do we as a species think this is important enough to spend the same amount of money we spend on a Webb Space Telescope, $14 billion, to look down at an ocean that sustains each and every one of us? Every second breath you take in this room came from the sea, and if that ecosystem fails, and it is struggling, you may not be able to take that second breath. So we're at a crucial moment. We understand lifeless worlds in space better than we do our own ocean. It's a moment where some of the natural systems that keep us alive on Earth are in danger of failing. We have discovered sentient, intelligent life in whales, but not bothered to learn how to communicate with them or care much for their survival. Not too long ago, we decided to put a man on the moon. This moonshot inspired technologies like the ones I shared today that can help explore and protect our blue planet. So I'm asking us, can we take another moonshot, but this time look down and wonder at what we have yet to discover? Let the ocean exploration inspire the next generation of space exploration. It may just save life as we know it. Thank you.
Thank you, Ved. I think we have time for one or two quick questions if anyone has them from the audience. Stace.
So I went down the rabbit hole last night on this fluid lensing thing, and I was looking for when we're going to deploy it to a spaceborne platform, and I couldn't find anything. So can you tell us how far we are from being able to access this kind of data, for instance, in Google Earth Engine?
So that data viewer, the prototype one on the wall there, which you can go and touch and zoom in, I encourage you to, that one we've just are launching for the airborne campaigns. We've proposed a few satellite missions, and NASA came back and said, aircraft are really where it's at, because you can fly under clouds, you can get the centimeter scale. A lot of the reef ecologists that we work with care about that resolution scale because that's how fast corals grow per year. So I'm happy with aircraft. I like them a lot more. They tend not to explode catastrophically when you put them up. And eventually I would like to put this on a spacecraft, but I think as these technologies start merging together and I keep reinventing the wheel every year, and it's incredibly frustrating because it takes me, I toiled away doing one map for 2 months, and then I came back with a new idea and a sensor and a drone, and now it's like 2 days, right? And I thought, why did I spend so long doing this? So stay tuned, keep supporting these efforts in Congress or with your local government, and don't accept that we should have this difference between what we can do in space and what we can do on Earth. Earth is just the coolest planet in the solar system, so it should get all the cool toys. That's what I think.
One more quick question.
I also just want to take a moment to thank my team who's up here of students. So they couldn't all come out. They really did want to come and see the prints, but they're here in spirit. Thank you.
Yes.
Okay, for our third speaker this afternoon, we are welcoming Johannes Mattes, who is a historian of knowledge and science based at the Austrian Academy of Sciences in Vienna. His research explores the natural sciences, including earth sciences, geography, cartography, zoology, and physics, from the 18th century to the 20th century, with a particular focus on the interplay between the scientific practices, visual culture, and the construction of natural spaces, especially subterranean environments. He has published widely in leading journals such as the British Journal for the History of Science, Journal of Historical Cartography, Centaurus, Episodes, and AHY. Research stays have taken him to Edinburgh, Leipzig, Oslo, Stanford, and Toronto, alongside a visiting professorship at the EHESS in Paris. His latest co-edited volume, Earth, Knowledge, History of the Earth Sciences as Histories of Knowledge from Routledge, will be published in autumn 2025. He's received several prestigious awards and grants and fellowships, including from the Marie Sklodowska-Curie Actions and the Alexander von Humboldt Foundation, as well as the Bader Prize for History of Natural Sciences. He currently serves as Secretary General of the International Union of Speleology and as a delegate to the International Science Council in Paris. His presentation is How Was the Subterranean Made Knowable? Mapping, Trust, and the Limits of Early Modern Vision. Join me in welcoming Mattes to the stage.
Thank you so much for this very honorable introduction. Yes, I feel very honored to be here. It's wonderful. I would like to thank all the organizers, the sponsors of this Congress to make it possible. And yes, I would like to start right away with a quotation. Next slide. How does it work? Here? Okay. I would like to start right away with a quotation by Alexander von Humboldt, who visited a cave in Latin America, today in Colombia, in Venezuela, the Cueva del Guaucharo, and he wrote about this visit in his diary. Quote, "We had great difficulty in persuading the Indians to pass beyond the anterior portion of the grotto. Men, they say, should avoid places which are enlightened neither by the sun, seas, nor by the moon, Nuna. We were obliged to employ the authority of the missionaries and the powerful influence of religion to combat these superstitious terrors. We saw with regret the Indians hold their eyes fixed on the ground and silent, showing that they were no longer guides, but strangers in a feared domain. This quotation opens questions like, what are the ethical and epistemic limits of acting in the name of science? What does exploration actually mean, especially in the context of caves and their cartographic representation? And finally, what politics of authority and participation are embedded in such practices? In recent years, scholars across STS, or Science and Technology Studies, and related fields have increasingly examined how exploration and epistemic frontiers are formed and understood. The focus has shifted from asking who achieved what and when to understanding how scientific knowledge is actually produced. This includes investigating how local knowledge about specific spaces is gathered, accredited, and internationalized, and how, through the use of scientific methods such as mapping and publishing, the ownership of knowledge can shift. In this perspective, the exploration of caves or subterranean spaces, because until the end of the 18th century, there's not so much difference made between the different kinds of spaces of the underground, should likewise be seen as part of a larger global history of knowledge, shaped by unequal power relations and the ways knowledge is shared, translated, and claimed. And here you see some of these characteristics of cave exploration. It's often about resource extractions. There are ideas of progress involved. There's also about masculinity and risk, invisibility, the exclusivity of the first look. Caves are, of course, the origin of humankind, but they're also natural history archives. And it's a lot about empiricism, imagination involved, and it's also about making these spaces way objective, accurate, because it's very hard to see a space which you can't see, because, I mean, with the light sources, it's very difficult. So, but also caves are also a social world. You can see here a cartoon of a surveying party in the Peak Cavern in England. And you can see here, for example, the scholar from the center. He has the measuring instruments, he has the mapping tools, the authority to accredit local knowledge through publications, and he also has the right to take samples. Here you have the local guide with practical knowledge and hands-on experience. And here, for example, you have the unacknowledged carrier who has to carry the whole weight of science. And of course, there are also a lot of invisible contributors considered as part of scientific infrastructure. This can be family members, often women who accompanied these parties to the entrance of the cave and so on. Well, this interest in caves in the subterranean world is also very much related to a new idea of the field and also scientific fieldwork. And here you can see an image of a mathematical physical cabinet in Vienna, and where the young archdukes of the Habsburg family are taught about geography. You see the globes, the different measuring instruments, and here in the middle there is a mathematician who was responsible for about 20 subterranean maps which were made, and he was commissioned by the Emperor Franz Stephan. He had the title emperor, but he was not the boss. The boss was Maria Theresia, and so he had time for science, and he sent this mathematician out to the empire to map caves, to sound lakes, to visit mines, and so on. So the whole subterranean world should be measured, surveyed, examined, and you see here also through the windows the landscape, which is now very important and should be measured. It's important for imperial rule. I argue that caves function also as boundary objects. stable enough to support shared reference, yet flexible enough to allow different communities to use and interpret them in distinct ways. Caves are more than physical spaces. They are zones where knowledge and uncertainty meet. Their entrances create transitional areas where light and shadow distort perception, heighten sensory awareness, and challenge orientation. And since Plato's cave allegory, subterranean spaces have been seen as laboratories for human perception. Historically, descending into caves often overwhelmed scholars, undetermined trust in their own observations and earlier reports. Well, what is complex? What is the difficulty to map a cave? It's the three-dimensional topography, which is very difficult to show on the map. Then you have the environmental conditions. It's very dark, it's humid, it's very cold, so it's not the best conditions for a surveyor to work. And there is this isolated nature. It's very difficult to communicate with the outside. And of course, what light sources they had candles, they had torches, but all the different light sources created different optical effects. So with a torch, you had a lot of smoke, so you can't see a lot of things, but it's very, it's very entertaining. Candles are very good, but they are, well, they give only small light source, little light, and so it's very expensive also. So candles were mostly used in churches. There is also the idea that the macrocosm of the earth is connected to the microcosm of the body. So there are theories which are interrelated. And of course, there is not so much difference made between natural and artificial cavities. So for the people in this time, it was often not so clear. And this was also used by artists. I have brought with me two pictures from the Grotto of Posillipo near Naples. The Grotto of Posillipo is an ancient traffic tunnel. And the same artist, mapped this street tunnel once as an artificial tunnel and one as a natural cave. And this is very, very typical for the 18th century. So in my talk, I ask, how did the creation of cave maps unite diverse actors, practices, and ways of knowing to give meaning to the hidden spaces of the earth? With regard to spaces of knowledge, I ask, in what ways did subterranean environments challenge conventional distinctions between observation and imagination in early modern scholarship? With regard to material and visual culture, I examine what roles did instruments, artisans, and translation practices play in shaping the scholarly meaning of underground phenomena? And with regard to authority and credibility, I ask, how did maps of subterranean spaces operate as tools of trust and persuasion under conditions of limited visibility? I argue that cave maps revealed far beyond what early modern surveyors could actually observe. Rooted in incomplete knowledge and ambiguity, the act of mapping was a creative translation process, merging observation and imagination and blurring the lines between natural, unnatural, and the supernatural. As epistemic tools, these maps enabled scholars and viewers to perceive and believe in structures otherwise invisible, shaping scientific reasoning despite uncertainty. And my argument draws on some 200 maps of natural cavities I examined in the previous years, and they were all produced before 1800 across Europe, North America, and Siberia. I haven't found any maps from Africa or Southern America. They start after 1800. And these maps serve diverse scholarly, artistic, economic, military, and even, if you like, touristic needs. And they were characterized by low standardization, so very, very diverse maps. And in the following talk, I would like to analyze this on 3 levels. First, I would like to look on liminality and hybridity, then on the techniques of trust, credibility building, and the end, to what extent these maps served scientific reasoning. And let's start right away with the liminality and hybridity of subterranean spaces. Subterranean spaces embodied liminality, where empiricism meet imagination, and mapping translated the unseen into knowledge. Two maps of the Kungur ice cave in northern Siberia illustrate this, showing different strategies for visualizing the invisible. The 1703 map of Semyon Remezov, commissioned by Tsar Peter the Great, guided viewers through a maze of icy chambers. You see it here on the top, on the left. Icy chambers filled with sacred icons, miraculous springs, and invented passages. Its imaginative additions creating a mythic geography, blurring empirical mapping with storytelling. Below, it's the same cave. In contrast, Johann Bergham's 1733 survey drawn during the Second Kamchatka expedition emphasized precision and uncertainty. Using compass readings and step counts, Bergham shaded unclear areas to indicate limited visibility and mark the explorer's route in detail. So he was much more open what he cannot see. And the other cartographer, well, he played with storytelling. And this map, the first one, it was very, very popular and circulated in various prints through Europe. So it was very, very known. Hybrid objects. Caves also challenge knowledge through the objects they contain, blending nature and culture. Prehistoric artifacts and natural formations such as stalactites spark debates about their origin. As hybrid objects, a term by Latour, they combined aesthetic, economic, and scientific value, circulating among scholars and collectors. In mining regions, local knowledge about underground spaces developed alongside natural history, where collect minerals and fossils prompted new ways of classifying the natural world. And you can see here on the left, actually, two maps. It's from the map collection MOL in Brno, so in Czech Republic. And actually, they show one mine on the right, and in the opposite, it's a cave. So they also are playing with this idea of culture, nature, art, architecture, and natural architecture. So, and actually this is also the same cave, once mapped by a French scholar, Mathieu Dumas, in 1783, here on the left-hand side. And Dumas was very convinced that this cave was just formed by natural processes. Mostly, he argued that it's erosion is the cause for this cave is formed. So he used, well, passages, he drawn the passages like it's, well, a natural cave. And the other guy, he was a Bohemian surveyor, Franz Sieber. He mapped the cave again in 1821, and he was convinced that it's a sort of hybrid cave, which was used as a quarry during Roman times, but there was a sort of natural cave also before. It was used as a quarry. So he also has drawn some artificial chambers. So, and both of them, of course, they used surveying tools. Yeah. Okay, let's come now to the second part of my presentation, technologies of credibility building. Early cave maps created meaning by turning fragmented impressions into coherent images. Their symbolic vocabulary, labyrinths, patterns, labeled chambers, and guiding lines did not simply depict space, but organized knowledge. By combining descriptive and emblematic elements, these representations bridge the gap between observation and imagination. They replaced sensory experience with a structured visual order that suggested reliability. And here you can see a map which was made in the mid of the 17th century by Studiosus von Alvensleben. He was a German student at the university, and he mapped the Baumanns Cave in Sachsen-Anhalt. And I mean, so you can't see any cave passages. It just used different objects or columns, stalactites in the cave to structure the whole map. And you can see here the visitors who are following a sort of a path through the cave, and they are passing one column, a column of a stalactite, and he used, he mapped it like a Greek column. Then you can see here on the left some stalactites which look like a monk, so he used also human faces to depict them, and the other one are different speleothems, flowstones, which he also, for this one, used small faces. Underground measurement was an uncertain practice, limited by darkness, humidity, and irregular surfaces. Yet instruments like compasses, measuring ropes, and simple step counts lent an air of precision. And you can see here, you can see here one of these surveying parties. Here the surveyor is in the back of one of these areas to draw the map. You can see a measuring cord, and here on the right-hand side, you can see what they had to do with the surveyor, because he need to go to a different part of a cave, so they tried their best to bring him there. But actually, when you are in a cave, you never see it like this, because their torches, their candles, you only see a few meters. So it's also, well, it's made, these pictures are made for the emperor to impress him, of course. And there are traces on map sheets of these measuring tools, like scales, coordinates, and explanatory notes, turned unstable data into systematic form. Longitudinal and cross sections offered new ways to envision the world beneath our feet, creating an artificial transparency that revealed the Earth's interior. Vertical representations in particular highlighted the ground's layers, linking physical descent with the pursuit of understanding the planet's inner structure. And here you see also a very scholarly map. You can see here measuring tools, here different objects which you can find in the cave. Here you see also my visitors. And here is Latin, a detailed explanation of all the different objects which can be found in the cave. It's only a small part here of the whole map. So it was made to convince the viewers, the readers of this map. So let's come now to the last part of my presentation, scientific reasoning. In the late 17th and 18th centuries, caves became key sites for localizing traces of Earth's history. In Leibniz, Protogaea, a revised map of the Baumannshöhle, the Baumanns Cave, you have seen it before in the previous slides, exemplified this shift, linking fossil locations and speleothems to geological processes. Through such mappings, subterranean finds were integrated into causal narratives of Earth's formation. And Leibniz actually used a map which was made already 80 years before as a layer, and here he inserted his fossils. Here you can find sediments of the cave to localize the findings and also to support his argument. Likewise, William Buckland's sections of Zollitenhöhle made geological chronology visible below the surface. By layering fossils, sediments, and stalactites, he turned caves into natural archives of Earth's history, visualizing his flood hypothesis by depicting fossils as relics of the biblical deluge. And you can see here on this map, here you can see fossils, which can be found that they're all covered by a layer of limestone. But we don't see any different layers in these fossils. So this was a sort of support for his idea that all the animals which lived in this cave, they were killed by the flood. And when they live for a longer period there, without one big event, you would have layers. And also the idea that you have a layer of limestone part is also to support this idea. But of course, there was no incidents. There were no evidence of this. He just advised his cartographer to depict it like that. Around 1750 to 1800, cave maps also began to serve as arguments about speleogenesis, the origins of caves themselves. For example, Nicolas Prémontier's 1765 survey of the Rouffignac cave employed 28 cross-sections to demonstrate the combined effects of erosion, tectonic action, and rock corrosion caused by the air. And you can see here the different cross-sections making very different distinct size. And this was really also used as an argument for his theory that there are different reasons combined that this cave is formed. So it's not only formed by erosion, not only by corrosion, but different actions. He also explained it partly by an earthquake which happened here maybe 1,000 years ago. So let's come now to my conclusion, and I would like to give you 2 take-home messages. My first question is, how did early modern cave maps transform empirical uncertainty into credible knowledge? Cave maps visualized what could not be seen. They translated partial fragmentary observations into persuasive spatial arguments, merging measurement and imagination. By depicting invisible formations and linking them to causal explanations, map makers established credibility where direct experience failed. Mapping thus became a means of making the invisible visible, transforming epistemic uncertainty into an argument of trust. And my second question is, what can early modern cave cartography tell us about the relationship between visualization and scientific reasoning? Early cave maps were not neutral records, but instruments of thought. They structured observation, suggested causality, and invited interpretation. In rendering subterranean process visible from fossil depositions to speleogenesis, these images shaped how naturalists understood the Earth's interior. They revealed that visualization was itself a mode of reasoning, a practice through which the unseen world was explored, explained, and ultimately believed. Thank you so much for your attention.
All right, a couple of quick questions.
Thank you for such a wonderful talk. That was really interesting. Can you tell us a little bit about, it sounded like most of these cave maps were being made for kings and royalty. What did they ultimately think of the end product, and were they happy with what they spent their money on?
Of course, they had an interest in money, as all the emperors and landowners have. I mean, most of these maps were really commissioned by landowners. Sometimes they were emperors, sometimes they were landlords or whatever. So very different people. And Yes, so there was an idea to find, of course, minerals in these caves. But of course, these landlords, these landowners had also an interest to develop their own country, maybe for tourists and so on. So there were different ideas. And most of these caves, they were in limestone regions, so karst regions. And what karst regions have in common, they are mostly not very fertile in agriculture. So there was always an interest to somehow to promote these regions when you want to map a cave or maybe open it to the public.
In the Habsburg Empire, there were a couple of mining academies where, they are quite old, like in Slovakia, Hungary, and the German states. Did people, professionals from those academies play a role in creating maps?
Well, of course. I mean, in the Habsburg Empire, you have Banska Stavnica, Chemnitz, and in Germany, it's not very far, it's Freiburg. Of course, these people were very much interested also. I mean, these mining academies were founded around 1760, 1770, so a bit later as these cave maps were done. But of course, there was a big overlap and there was an interest. As I said, so interest in mining was often combined with an interest also in natural cavities.
I'm wondering, apart from this research, where is there other use for the caves? Like today, people do recreation. What were people interested in terms of visiting? Did they want to see, learn about the science, or was it different back then? And like, did people use it as shelter? Or?
Yes, there was a very, very diverse use. Sometimes from the local population, it was caves were used as storage rooms because it was very cold and you had no tools, to cool your milk, for example. So it was very, it was used. Of course, caves were also used for as an source for different resources. For example, for sulfur, which was used for gunpowder making. But of course, the local population also used stalactites to produce sort of medicine, which was used for the cattle, but also the people took different sorts of stalactites. So that was very common. But of course, there were also recreational aspects, but this was only limited to noblemen. So it was very common in the 18th century to go there, a sort of, a party of rich people, to drink wine in the cave, to eat, and so on. That was quite common. So, especially in Italy in the 18th century, where caves played a big role. Yeah.
Thank you, Johannes. So I think we're going to take a quick 20-minute or so break upstairs in the Bender room, which is, if you weren't here yesterday, you can go out this door up one floor. You can also take the elevator over here up to the 5th floor. We're going to come back down here in 3:30. Let's call it 3:35. We'll probably start a little bit late. So anybody that's in Zoom that's waiting, we're gonna start maybe 5 minutes after, and for our final presentation. So